Hello, everyone. Today, we are going to continue with solving some linear algebra problems. So I think this week your homework is about eigenvalues and eigenvectors. So also I'm going to mostly focus on that. So I'm going to solve some problems similar to things you would see in homework or potentially in the exam. So let's just start. Whenever we have a linear map like T from a vector space to itself, T from V to V, we can look at this equation. We can look at vectors like U. So U is a vector and lambda is a scalar in the field. For example, in R or in C, whatever the field is. And we can look at such vectors and numbers such that T of U, the image of this vector U, is equal to lambda times U. So the picture I have in mind is something like this. If we have a vector space, say R2, for simplicity, let's just do it over R, and again R2 again, and then we have a linear map T from R2 to R2. It means U is a vector like this, such that T of U is another vector in the same direction. So here the field is the set of real numbers. So this number can be something positive or negative or even zero. So for example, if this number is 2, it means we just get 2 times U. Or if this number is negative, we get, for example, minus U here. Right. So it means in that direction, the linear map preserve the vectors in that direction, right? Doesn't change the direction. Such a vector is called an eigenvector. And this number is called an eigenvalue. So in order to define this concept, we don't need to only focus on finite dimensional vector spaces. This concept of eigenvectors and eigenvalues, they make sense even over infinite dimensional vector spaces. And probably you're familiar with some of them already. So for example, suppose I take the field to be the set of real numbers. And suppose I define V to be real valued functions on R. So say, well, for simplicity, let's say smooth or differentiable. Let's say differentiable functions like f from R to R. Okay, this is a vector space over the field R, right? And let's define this linear map T from V to V. Let's define T of any function f of x. Let's define it to be f prime of x. Okay, so maybe a better way to write this is that T of any function f is derivative of f, df with respect to dx. So this is a linear map. We can check that it preserves the linear structure. And one might want to look for the eigenvalues and eigenvectors. What are the eigenvalues and eigenvectors of T? So that's the question. We want to find the eigenvalues and eigenvectors of this linear function defined on a vector space which itself is infinite dimensional. So think about that for a few minutes. And if you have any question in the meanwhile, you can ask me. So let's first write down the equation. So the equation for such eigenvalue and eigenvector should be something like this. This function acts on f, we look at t of f, and t of f of x is f prime of x. And on the other hand, we want it to be some lambda times f of x, right? This is the equation describing an eigenvalue and an eigenvector. So do you know any function which satisfies this property? Maybe let's look for special cases first. So if I take this number to be 0, it's kind of a trivial problem. Then this equation, so I would write down the equation here, f prime of x would be, in this specific case, would be 0 times f of x, which just means it's 0. Okay, we have an answer. It's very close to being correct. I guess it is correct.
Isn't
we
it?
Get there.
Can I go?
Yeah.
Well, wouldn't the C and the K be the same thing?
That's a good thing. So you are referring to the message, right? In the chat.
Yeah.
Yeah. Okay. Yeah. We would look at that. That's a good one. Yeah. So let's consider first this maybe more trivial case that f prime of x is 0. What does it say about f? What are the functions satisfying this property? Well, just the constant ones, right? Constants. It means f is equal to a constant number, like 2, 0, or something like that. Now, if I take this eigenvalue to be 1, you might have seen this function before, a function which its derivative is equal to itself. I'm assuming you all have seen this function before. This is the exponential function. F of x equals e to the x, right? Derivative of this function is equal to itself. Derivative of e to the x is equal to itself. But there are more, as we can see in the chat, and as we heard, yeah, there are more functions of this kind. So, for example, 5 times e to the x has the same property too. So if I define f of x to be 5 times e to the x, what is the derivative of f? Well, 5 is a constant. It would just stays there as the coefficient, and derivative of e to the x is e to the x. And as you can see, it is equal to f of x. And that's true in general. If you have a vector v in general, such that t of v is equal to lambda times v, for any non-zero element in the field, like a, some other number, non-zero number in the field, we can see that t times a times v is equal to a times t of v, because t is a linear map. A comes out of the function. And we are assuming v is a vector which is eigenvector with eigenvalue lambda, so tv is equal to lambda v. But on the other hand, remember, over a field, a times field and a vector space, a times lambda v is equal to a times lambda times v. And because we are in a field, the field is commutative. So a lambda is equal to lambda a times v. And again, this is equal to lambda times a times v. Now, if you look at this equation, we started here, t of av, and we ended up here. And this means t of a vector is equal to lambda times that vector. So that vector is an eigenvector, and its eigenvalue is lambda. Same eigenvalue as v. So whenever we have a vector with some specific eigenvalue, if you multiply that vector by a non-zero element in the field, we get another vector with the same eigenvalue. So therefore, the phenomena we see here is something natural. But for more general case, so generally, we want to solve this equation for lambda in the field f. Okay, so one natural guess would be just generalizing the exponential function. So in the chat, we see one suggestion: f of x equal to c e to the kx. So what is k here? Is it, I think you mentioned k is the same as lambda, I guess, if I heard you correctly. Oh, for any c. So, well, let's take it to be k. Let's see if let's see what we would get. Yes, c and k are two scalars. Okay, let's take derivative of f. So f prime of x is equal to c k e to the kx. So we can see f prime of x is equal to k times c times e to the kx. And this is the function f itself. So if lambda is equal to k, we would get an eigenvector. That is correct. It's okay. The answer to the comment, yeah. So so that is correct. So maybe rather than k, I would just write lambda now. So these functions are the eigenvectors. Thinking about them as a vector in this infinite dimensional vector space, they're eigenvectors with eigenvalue lambda. So what are the possible values for the eigenvalue? What can we choose? What are the possible values for this lambda here? Does anyone want to give the answer to this question? Can lambda be anything, or there are restrictions?
It can be anything.
That is correct. It can be anything, because this function e to the lambda x here, we can just write down any number. E to the x is defined for anything, and as our computations show, derivative of that is always equal to lambda times itself. So what are the eigenvalues of this linear operator t? Well, the eigenvalues are equal to the whole set of R. The eigenvalues, we have all the set of R completely as the set of eigenvalues. What are the eigenvectors or eigenfunctions? They are these things, functions of this form. So, but the answer, but the thing we should answer now is that all, or is there any?
I was just wondering, what if lambda equals 0, then the derivative. Oh, I see. If lambda equals 0, then the derivative is just the derivative of constant, which is 0.
That
Isn't
is
lambda
correct.
not allowed to be 0?
Yeah, so it depends on your definition. Usually we would take it to be non-zero. That is correct. Because I was just analyzing the equation, we wanted to see what would happen if lambda is 0. But
Right.
that is correct. For the definition of eigenvalue and eigenvector, we would look at the non-zero eigenvalues and eigenvectors.
Got it. Thank you.
Yeah. So is there any other function? Say f of x, such that we still have this thing, such that the derivative of f is equal to lambda f. Is there anything, sorry, I missed f of x. Is there any other function, or did we find all of them? That's the important question. So does anyone have any answer? What do you think? Do you have any guess?
I would say that there are no other functions.
Yeah, that is correct. That is correct. So this property, yeah, that is true. This property really nails down the function f to the thing we got. So maybe first answering some easier question, let's consider only the case lambda equals to 1. So suppose we want to look at this function f prime of x equals to f of x. We know a multiple of e to the x is a solution here, but is there anything else which is answer to this, which is a solution to this equation? The answer is no. So the only solutions to this equation, they are of the form a constant times e to the x for this special case. Okay, let's see the proof to that. So suppose there is, suppose I'm going to prove this by contradiction, okay? So suppose there is another function gx such that g prime of x is equal to gx, and this is not of this form, c times e to the x. Now, I can multiply this function by e to the minus x. This is a new function. I define this new function h of x to be e to the minus x times gx, right? I'm just defining it like that. So let's see what is derivative of h. So the derivative of h of x is equal to, well, first I should take, this is the product rule, right? I should first take derivative of the first function, which is just minus negative e to the negative x times g of x plus, and then e to the minus x times g prime of x, which is equal to, well, negative e to the negative x gx plus e to the minus x times g prime of x. But what is g prime of x? Well, we assumed g prime of x is equal to g of x. We assumed g is a solution to that equation. So rather than g prime of x, I would just write down g of x. And as you can see, these two cancel each other, right? So it is equal to 0. Therefore, h prime of x is equal to 0. If h prime is equal to 0, it means h is a constant. Is constant. Let's show it with a, just a constant, just a number. But what is h? Well, here we defined h to be e to the minus x g of x. And that's a constant a. Therefore, g of x is just 1 over a e to the minus x. 1 over a is another constant. I show it with c. So g of x is c times e to the minus x. So there is no other function. G of x has to be of the same form. Maybe it wasn't even necessary to say I'm proving it by contradiction. I could say suppose g is any function satisfying this thing, and then we would get to this point to see g of x is equal c times e to the minus x. So that's it. That's the only thing. And the same, exactly same argument hold for more general case. So if I want to prove, this equation, the only solutions of this equation are of the form ce to the minus, lambda x. If I want to show that, the idea would be, suppose there is other solution to this equation, and this time rather than multiplying it by e to the minus x, I would multiply it by e to the minus lambda x and define that to be h of x. And again, like the previous case, we would take derivative of that. We would see the derivative becomes 0 using product rule. And then we would understand g of x e to the minus lambda x should be a constant. I would call that constant a. So again, I would see gx is equal to a e to the lambda x. Yeah. So so that's it. Did I make any mistake here? So sorry, this one wasn't 1 over a. This one was also a. Doesn't matter. It's just a constant. So that's the way.
To the x, right?
Sorry?
A e to the x positive?
Yes, a e to the x. That is correct. There was a small typo mistake.
How do you know that if h prime of x equals 0, then h of x equals a? Don't you need to prove that as well?
Well, I mean, a is a constant. So what we know is that if derivative of a function is 0 for a differentiable function, that function is constant. So are you asking why that's true? Why if derivative of something is 0, it is constant?
Well, I understand because then it just doesn't change, right?
That is correct. So there is a more, yeah, well, intuitively that's correct. There's a slightly more rigorous argument for that. So the idea is that if you have a function, say differentiable function or smooth function from R to R, if it's not constant, it means there are 2 points, say x1 and x2, which the value of the function at those 2 points are different, right? If the function is not constant, it means there are 2 inputs, which they give us different outputs, right? And so you can look at the function here. And the point is that there was, if you remember, we have a theorem in calculus which says f of x2 minus f of x1 over x2 minus x1 is equal to, for any x2 and x1, is equal to derivative of the function somewhere between them. So at some point x, we have this equality, right? F of x2 minus f of x1 over x2 minus x1 would be derivative of the function at some point. So if you have forgotten this, you can take a look at the calculus. It was one of the theorems we had for derivative. And the point is that because we know derivative is always 0, so this right-hand side is 0. So we have a fraction. If it's 0, its numerator has to be 0. So f of x2 minus f of x1 is equal to 0, which means f of x2 is equal to f of x1. For any x1 and x2, f of x2 is equal to f of x1. Means f of f is the same for all. Let's remember how we compute eigenvalue of a matrix. So suppose I have a matrix A given matrix. Let's choose a simple one, 2, 1, minus 3, 0. And I want to compute its eigenvalues. So eigenvalues of A. How can I do that? What are the eigenvalues of A? Well, it's a simple question. You can just unmute yourself and answer. What is the method of computing the eigenvalues of a matrix? Do we know that?
You find the matrix for A minus lambda I for some lambda, and then find when that has 0 determinant.
That is correct, yeah. Nathan, you wanted to say the same thing?
Right. I was going to say that you could put A into upper triangular form, and then you could read off the diagonals. I mean, I guess they're kind of similar methods.
Yeah. But that is true. So here so it's a question if we can always we should answer if we can always do that or not. But yeah, definitely that's also a method for computing the eigenvalues. So let's do that. So if we have a matrix A, we want to look at for eigenvalues and eigenvectors. We should look at vectors like V such that AV is equal to lambda times V. Okay, and it means I can, if I take the right-hand side to the left-hand side, it means AV minus lambda times V is equal to 0. Okay. Now, lambda times V is the same as lambda times identity matrix times V, right? Because identity matrix times any vector is the vector itself. So I can replace the vector V with the identity matrix, right? So it means if I factor V, it means matrix A minus lambda identity matrix times V is equal to 0. Correct? So think about this whole A minus lambda V as a linear map or another matrix, let's say. So it means TV is equal to 0, which means V is in the kernel of T. So it means, well, I'm assuming V is non-zero itself. So it means T has non-trivial kernel. There is a non-zero element in the kernel of T, right? So when we know a matrix has you can multiply a matrix by a vector which is non-zero and you get 0. That tells us something about that matrix, about the determinant of that matrix. What is it? What is determinant of a matrix which has non-trivial kernel? By kernel, I mean null of T. Maybe you're more familiar with that word. Does anyone know when you have a matrix and you can multiply that matrix by a non-zero vector to get 0, it means that is correct. Yeah. Determinant of that matrix is 0. Not determinant of A. Yeah, you're right. I think you mean this T here. Yeah, determinant of T is 0. But T itself is A minus lambda times the matrix identity. So this determinant is 0. Now the point is that A is a given matrix. We have A. Identity is also a given matrix. It's just 1, 1 on the diagonal. Lambda here is the unknown. Lambda here is the unknown. So I can think about it as a variable, you know, like X, the unknown, the variable. If I do that, this equation would be a polynomial in lambda. So this equation would be a polynomial in lambda. So for example, the matrix we chose, 2, 1, minus 3, and 0. We can look at this polynomial for that matrix. So it means look at A minus lambda identity, which is A, this is A, minus lambda times identity, this is a identity matrix. This is equal to 2, 1, minus 3, 0. And I would multiply identity matrix by lambda. It would be lambda times 1, lambda times 0, lambda times 0, and lambda times 1. And then, you know, we subtract them component by component. So it would be 2 minus lambda, 1 minus 0, minus 3 minus 0, and 0 minus lambda. And what we want is, we want determinant of that matrix to be 0. So determinant of A minus lambda I being 0 tells us determinant of this matrix 2 minus lambda, 1 minus 3 minus lambda is 0. So what is determinant of this matrix? It's 2 minus lambda times minus lambda minus negative 3 times 1. That's equal to 0. If we do the multiplication, we get lambda squared minus 2 lambda plus 3 is equal to 0. So we get a polynomial for lambda. And then if we solve this polynomial, the values are eigenvalues of the matrix, right? If I solve this equation, I would get the eigenvalues. So what are the solutions? There are 2 plus minus square root of 4 minus 12 times 2 over a. As you can see here, under the radical, we have a negative number, right? It means no real eigenvalue. So if we are looking for eigenvalues in R, there isn't any. Okay. Now going back to this equation, this is an important equation. This equation is the same as this one. This is called the characteristic polynomial. Now, I want to tell you an important theorem about this, and it's called Cayley-Hamilton theorem. Cayley-Hamilton theorem says A satisfies its characteristic polynomial. equation, as an equation actually. What does that mean? Or characteristic equation. What does that mean? So here, okay, let's see what does that mean in this example. So A was equal to 2, 1, minus 3, 0, right? And the characteristic polynomial or characteristic equation was lambda squared minus 2 lambda plus 3 equals 0, right? The interesting thing is that if you, well, we know this lambda is a real number, right? It's not a matrix, it's a real number. Lambda should be something like 0, 1, something like that, which in this equation doesn't have any solution actually. But for a moment, let's forget about that and plug in the matrix there. So let's plug in the matrix instead of lambda. We get the matrix A squared minus 2 times matrix A plus 3 equals 0. But plus 3 doesn't make sense, right? Because here we have matrix and 3 is a number. We can't add 3 to a matrix. So in order to this thing make sense, we always write it as yes, that is true. 3 times the identity matrix. And the theorem says this thing holds if you instead of lambda, if you just plug in the matrix A, you would get 0. So let's try that here. What is A squared? Let's try to see if we did it correctly. Okay, it's 2, 1, minus 3, 0, 2, 1, minus 3, 0, and it's equal to 4 minus 3, which is 1, 2, minus 6, minus 3, if I'm right. And then minus 2a is equal to minus 4, minus 2, 6, and 0. And then we have 3 times identity. Let's see if we did it correctly. So we should add these 3 matrices. The first one is a squared. The second one is minus 2a, and the third one is 3i. And their sum is supposed to be 0. What is their sum? So here we have 1 plus minus 4, which is minus 3 plus 3 is 0. Yes. So here we have 2 minus 2 plus 0, it is 0. Good. Minus 6 plus 6 plus 0 is 0. Yeah, that is also true. And minus 3 plus 0 plus 3 is equal to 0. So their sum is really this 0 matrix. So any matrix satisfies its characteristic polynomial. Okay. Now I want to use this theorem. Maybe I should say first another theorem. So we know if we look at this polynomial a minus lambda I, and if we compute its determinant, if we set it equal to 0, we get a polynomial. Now, and as I said, a itself, if we think about it as a matrix polynomial or matrix equation, just thinking about lambda as a matrix for a moment, we know matrix A itself satisfies that A is a root for that polynomial itself. Now, there is an interesting theorem. So if you find another polynomial which A satisfies, if you find another polynomial which A satisfies, there is, so let's say I found another polynomial. Let's say in the previous page, we saw A satisfies this equation. Maybe someone else finds another equation which A satisfies. The interesting thing is that between all these polynomials, there is one polynomial which A is a root of that, and that polynomial divides every other polynomial. So, so you can look at all polynomials which A is a root of them, And there is one polynomial up to multiplication by constant. There is one polynomial which is in some sense is the smallest one, has the lowest degree, A is a root of that polynomial, and that polynomial divides every other polynomial which A is a root of. Okay, that polynomial is called minimal polynomial of L, of the matrix A. So if I call this characteristic polynomial, it's a polynomial. If I call it P of lambda, and if I call this polynomial M of lambda, P of lambda would be this M of lambda times another polynomial. So in other sense, M of lambda divides P of lambda. Okay, so maybe I should stop here. Do we have time still? Yeah, a little bit. So, okay, what is the question? So M of lambda, does it take out the repeated eigenvalues? Yeah, so that's a good thing. So it's a good practice to try to compute the minimal polynomial. It is correct that it's not necessarily takes out all repeated eigenvalues, but it has all the eigenvalues, and we should find the multiplicity, so the appropriate multiplicity in the minimal polynomial. I want to give you an example. Actually, I had decided about some interesting question using minimal polynomial. So suppose we have a matrix A, 3 by 3 matrix A, real valued matrix 3 by 3. Suppose I know A cubed is equal to identity. That's the only thing we know. And the question is, what are the eigenvalues of A? That's the question. So think about this for a minute. I want to use this theory of characteristic polynomials and minimal polynomials to tell you how we can solve these questions. Okay, so if the question is very similar to a question in homework, maybe I wouldn't solve this one. It's okay, I wouldn't solve this one here, but when you do your homework, you can also think about this to see if your solution would also help to solve this one, and if not, I would solve it next week. I don't want to spoil your homework for you. I know you want to think about that. So let's keep that, and let's do another question.